Okay, so today I wanted to discuss homotopy category of a model category and the fact that model categories are saturated. So let me start. So let me give the topic. Homotopy category. So recall the definition of homotopy category. So assume that M is a model category. So this denotes just the category of small model categories. Then by HOM, we denote the localization in a class of weak equivalences. So this actually makes sense for any pair of a category and subcategory. And on objects, well, have the same objects as in the model category. And on morphisms, we have a description. So the set of morphisms between two objects consists of various zigzags like this, where the arrows that go backwards belong to weak equivalences. And we have a functor, localization functor, which is identity on the objects, and which sends a morphism to a zigzag, which consists just of this morphism. So this is just a basic construction of localization of basically any category. For example, it makes sense for homotopical categories or for model categories. Now, let me recall the notion of fibrant and cofibrant objects. So assume once again that M is a model category, and we say that X is a cofibrant object, which will be denoted like this. So M sub C is a full subcategory spanned by cofibrant objects. X is cofibrant. The unique map from the initial object is a cofibration. Dually, X is fibrant, so this denotes a full subcategory spanned by fibrant objects. If the unique map to the terminal object is a fibration. And we have two elementary properties of fibrant and cofibrant objects, namely that if we have a cofibrant object and we have a cofibration, then Y is also cofibrant. And dually, if X is fibrant, sorry, that would be Y. If Y is fibrant and we have a fibration, then X is also fibrant. So let me also introduce MCF, which is just the intersection of full subcategories spanned by fibrant and cofibrant objects. i.e., it consists of objects which are both fibrant and cofibrant. Now we have the following rhomboid, which already appeared in the introductory talk. Namely, we have a rhomboid of inclusions of full subcategories of the model category M, which induces, and we have functors in opposite directions, opposite to inclusions, which are given by functorial fibrant and cofibrant replacements. So goes like this. And since fibrant and cofibrant replacement preserves weak equivalences, we have the following proposition. Assume that this sign is used to replace let. Let M be a model category. Then the full subcategory MC is a left deformation retract of M, which means that MC is a full subcategory of M, such that we have a pair QS, where Q is a functor from M to MC. Q is just the cofibrant replacement. And it is a homotopical functor, which means it preserves weak equivalences. And we have a natural transformation S, which goes from the composition of the inclusion functor from MC to M and the functor Q to the identity functor on M. And this natural transformation is a natural weak equivalence, which means that the components of this natural transformation are all weak equivalences. Dually, MF is a right deformational retract of M, and the fact that it is a right retract is just means that we have a natural transformation in the opposite direction. Finally, category MCF is a left deformational retract of MF, and the right one for MC. Now, this immediately implies in corollary, which was also stated in the introductory talk, namely that this rhomboid of homotopical categories actually induces equivalence on the level of homotopic categories of these homotopical categories. Okay. So now the bulk of this talk will consist of explaining how to easily describe this category here. I also mentioned basic idea behind it in the introductory talk, but now we will discuss it in more detail. So now I will discuss various homotopy relations on the maps in the model category. So the first one here is left homotopy. When we say that F is left homotopical to G, if they're both go from one object to another, they're maps between the same object, and we have a cylinder object, which I will this time define a bit differently. So here we say that a cylinder object is just something that is weakly equivalent to B, and such that the inclusion of two copies of B into, well, not the inclusion, the map from two copies of B to B prime is a cofibration. So we actually can consider a canonical cylinder, B times I, where we require this to be a trivial fibration, but instead we will consider a weaker notion of a cylinder where we only require it to be weakly equivalent to B, not require the map from B prime to B to be a trivial fibration. So the notion of left homotopy then is that for some cylinder object we have a map such that the map H such that it fits into the following commutative diagram, where I0 and I1 are just maps of the components of this co-product. So dually, the notion of right homotopy equivalence, right homotopy is defined using the path object, well, a path object. So we have an object X, we have a map from X to X times X, and we require the path object to be something that vibrates over X times X and is weakly equivalent to X. So here we also could require this to be a trivial cofibration, but not necessarily. And the diagram for right homotopy is dual. So we have a map K, which is the right homotopy, which fits into the following diagram. So here we have pi0 and pi1. Pi0 and pi1 are projections from X prime to the factors in the product. Finally, we say that F is just homotopical to G if F is both left and right homotopical to G. And we say that F is a homotopy equivalence if there is a homotopical inverse of G, of F, such that, well, the meaning of the combination of words homotopical inverse is that GF is homotypical to, well, identity map on one end of F. So it is homotypical to the identity map on tail of F, and FG is homotypical to the identity map on the head of F. Okay, and finally, the usefulness of these two relations on morphisms in model category is that if F is left or right homotopic to G, then in fact under localization they become equal. So this is the reasoning behind introducing these notions. And the converse also holds under converse also holds under certain assumptions B and X. Okay. Here's that, and let me formulate a proposition which further explains properties of left and right homotopic maps. Assume that once again have a model category F and G are maps from B to X, and so the first part states that if F is left homotopic to G and we have H which goes from X to Y, then HF is left homotopic to HG. And dually, if we have F which is right homotopic to G, and we have a map H which goes from A to B, then FH is right homotopic to GH. The second part states that under assumption that X is fibrid, F is left homotopic to G, H goes from A to B. We have the, well, converse statement, namely that the precomposition with H of F and of G are also left homotopic. And dually, well, you can guess the dual statement. Okay, the third part of the theory of this proposition states that if B is a cofibrant object, then left homotopy is an equivalence relation on the home set between B and X, and dually the same thing for right homotopy under assumption that X is fibrant. Okay, the final part of this proposition states that under assumption that B is cofibrant, H is either a trivial fibration or H is just a weak equivalence, but X and Y are both fibrant. It implies that the induced map on quotients of home sets under the equivalence relation is a bijection. So if we replace X by something that is weakly equivalent to X and also the map is fibration, then the class, the set of equivalence classes of maps under left homotopy does not change. And dually, we have the same statement for fibrant X, trivial cofibration, or weak equivalence between cofibrant objects. Okay, so I lied, it was not the final part. Here's the final part of this proposition. So assume that B is a cofibrant object. Then the fact that two maps are left homotopic implies that two maps are in fact right homotopic. Moreover, if X is any path object, for X, then there is right homotopy which uses this particular path object. And goes from F to G. And dually, we have the same statement for fibrant X and right homotopy, which the fact that that two maps are right homotopic implies that they are left homotopic, and for arbitrary cylinder object for B, there is a left homotopy involving this cylinder object between the maps F and G. Okay, so this is a quite important proposition, and now we will prove it. So I start from the first part is almost immediate. So we just need to compose the homotopy with the map H. And we will obtain the desired homotopy between compositions. So here it is quite straightforward. Okay, so let's move on to the second part. Assume that X is a vibrant object, F is left homotopic to G, and H goes from A to B. We want to prove that FH is left homotopic to GH. For this, consider the homotopy between F and G, left homotopy, which goes from some cylinder object for P prime to X. So this is a left homotopy between F and G. Since X is vibrant, we can assume that, in fact, the map from B prime to B is a trio of vibration, not merely weak equivalence. Why is that? Well, if we have just a weak equivalence from B prime to B, then we can decompose it as well, trivial cofibration followed by vibration, which is also trivial because of 342 property. And B2 primes is thus also a cylinder for B. And now, since X is vibrant, there is an extension of a homotopy. So there is an extension of homotopy H from B prime to X to H prime, which goes from B2 primes to X. How this works? Well, we just consider this map H, consider the vibration to the terminal object, consider the trivial cofibration, which exists by the definition of B2 primes, and consider the unique map to the terminal object. Then here there exists a lift, which is precisely the required homotopy H prime. Thus, we can assume that B prime to B is a trivial vibration. Now, consider a cylinder for the object A. I have the folded map here. And we have some A prime here. We can find the lift in the following diagram. So I don't know, let's denote this by S. And and we had a map H, so this is just HS. This is a trivial fibration. This map, wait a minute. Yeah. So this map here exists because the moment. Well, this is just the composition. So we had maps from B, well, 2 copies of B to B prime, and then we have a map from 2 copies of A to 2 copies of B in an obvious way. Yeah, so this is just the composition. And here we have a lift because this is a cofibration and this is a trivial fibration. So we have lift, let's say K. And now HK is the desired homotopy between FH and GH. The dual statement is proved by reversing arrows and considering the path object instead of the cylinder. Okay. Now let's move on to the third part, where we want to prove that the left homotopy between maps is an equivalence relation under assumption that B is cofibrant. So first of all, observe that this relation is always flexive and symmetric. So why is it symmetric? Well, just because if we have a left homotopy from F to G, we can just flip 2 bottoms of the cylinder and obtain a homotopy from G to F. And it is reflexive because we can consider the following diagram, where S is the weak equivalence between B prime and B. So this proves that F is left homotopic to itself. Now it remains to prove transitivity, and it's a bit tedious, but well, actually, I'll leave that. The basic idea is that one wants to construct a larger cylinder from 2 smaller cylinders, basically just by gluing them together. However, if in topology this construction worked directly, I mean, if you glue 2 cylinders, then you just obtain a cylinder of twice the length. But here, things are a bit more tricky because we lose the condition that the inclusion of bottoms of the cylinder should be a cofibration. However, it can be remedied, and I will show you how. So Sorry. So when B be a cofibrant object, then we want to show that if F is left homotopic to G and G is left homotopic to H, then F is left homotopic to H. Assume that H large is left homotopic between F and G. And H prime is a left homotopy between J and H. We want to consider the following object, just a push out along B of B prime and B two primes. The maps here are I1 and I prime 0. So it can be visualized using the following picture. So here we have I1 of B, and here we have I0 prime of B. So this part here is B prime, this part here is B2 primes, and this altogether is C. So we have a map from two copies of B to C, denoted by J0 plus J1, and C is weakly equivalent to B. So first of all, how we define J0? Well, visually it is quite clear. We just need to take I0 and compose it with the inclusion of B prime into C, which is exactly what we do. So take B to B prime, and then to C. J1 is defined in a similar manner. We take I1 prime, load it into B2 primes, include B into B2 primes, and map it to C. So this S-color graphic is induced by S and S prime. Let's know it's star. So yeah, and this implies that S calligraphic is in fact a weak equivalence. Well, why is that? Basically because I1 and I0 prime are both trivial configurations, in fact. And thus, by 342 property, we have that S is always is also a weak equivalence. Let me maybe draw it in a bit more detail. First of all, observe that since B prime is a part of the factorization of the folding map, if we restrict it to just one copy of B, we have a factorization of the identity map on B, and we have here, for example, I don't know, I0 or I1. this is a cofibration. And since this is a weak equivalence and the identity map is also a weak equivalence, I0 and I1 are both weak equivalences. Yeah. So now, knowing that, we can see that here we have commutative. We have a commutative diagram like this, and here we have two weak equivalences. Thus, applying this to, yeah, and also recall that in the previous talk we established that trivial cofibrations are stable under push-outs, which implies that this map here is also actually a trivial cofibration. So considering these three maps and using the 342 property, we see that the map as calligraphic from C to B is in fact a weak equivalent. Okay, so all of this is great, and we almost got the required homotopy between map F and the map H. We have only one difficulty. So what we have so far, we have map J0 and J1 from B to C, and we indeed have the map F and the map G here, and we have a map from C to X, which is induced by the coproduct of two homotopies, H and H prime. However, C is not a cylinder object because J0 plus J1 does not belong to cofibrations. So we have to fix this. How we do that? Well, we just consider the following factorization. So we have a map from B with B to C, and we factorize it as B with B to C prime to C. Here we have a cofibration and a trivial fibration. Now it becomes clear that C prime is a cylinder for P, because we already had weak equivalence here, and here we just add another weak equivalence. Now it just remains to see that the composition of this map is the desired homotopy between a homotopy F and F and H. And here I also should have written H, of course. Okay, So, well, we've proven the third part of the theorem, and now I will make a short intermission to talk about Ken Brown's lamp. So let me briefly explain what it is. So once again, assume that we have a model category, and we also have C, a relative category, meaning that it is a pair CW where W satisfies the E42 property. And assume that we have a functor f from M to C is a functor such that f maps trivial cofibrations between cofibrant objects into weak equivalences in C. Then, in fact, f maps all weak equivalences between cofibrant objects into weak equivalences in C. Well, and we have a dual statement which says that if we have a functor which maps trivial fibrations between fibrant objects to weak equivalences in C, then in fact it maps all weak equivalences between fibrant objects to weak equivalences in C. So let's prove this statement. Assume that we have a morphism alpha from A to B, which is a weak equivalence between cofibrant objects. And consider the composition of the following form. So have full product of A and B. We have a map alpha and the identity on B, which goes to B. And we decompose it like this. Okay. So now we observe that the co-product of A and B obviously fits into the following push-out diagram. And this in turn implies that since cofibrations are stable under push-outs, that the map from A and B to their co-product are both cofibrations. So let's denote them I1 and I2. Now we see that the composition of Q I1 and Q I2 are both weak equivalences. Why is that? Well, we know that A is weakly equivalent to B, and so we just use the 342 property to see that this is the case. So well, maybe in more detail, have map. Yeah, so we see that A to C fits into this diagram, and hence it is also a weak equivalence. For QI2, it is even more simple. Okay, so we also observed that QI1 and QI2 are both cofibrations. Well, for obvious reasons, we have a composition of two cofibrations. And so their images under the function f both belong to this subcategory W. It means that since f of PQI2 is equal to f of the identity on B, which is also obviously in W. So I'm sorry, maybe I did not introduce it here. P is a map from C to B. So PQI2 is clearly an identity on B because from the very definition of Q and P. And so we see that by 342 property for the subcategory W, so 342 for W implies that f of P is also in W. This in turn implies that f of alpha equal to f of alpha QI1 is also in W, which was the point. Sorry. PQI1. This is also from the definition of PNT, because it factorized this co-product map between alpha and the identity on B. Okay, so this is the proof of Ken-Brown's lemma, and now we can apply it to prove the fourth part of the theorem, sorry, of the proposition. So assume that we have a weak equivalence between vibrant objects in model category M. Then the fact that the induced map, sorry, maybe I should recall what we're trying to prove here. So we're trying to prove that the induced map here is bijective. And to prove it, it is actually sufficient to prove it only for the case where H is a trivial fibration. Why is that? Well, that's because we can apply Ken-Brown's lemma for a functor MB something modulo left homotopy equivalence, considered as a functor from the model category M to the relative category consistent of sets and isomorphisms between them. So now we can assume that H is a trivial fibration, and we need to prove that H star, which goes from this set to this set, is a bijection. Well, as it turns out, yeah, first of all, observe that both these sets are well defined, and the map between them is also well defined by parts 1 and 3 of the proposition. So first of all, we will show that H star is surjective. Assume that we have a map F prime from B to Y. Since B is cofibrant, we can consider the following diagram. And here it is a trivial fibration, hence there is a lift which shows that H is in fact an epimorphism. So it is an epimorphism even without passing through homotopy classes of maps. Now, let us show that if we have two left homotopic maps from B to Y, then they were in fact homotopic before we composed. Okay, well, let me write this down. So assume that HF is left homotopic to HG. Then we want to show that F was in fact left homotopic to G before we composed it with H. So consider the left homotopy H from B prime to Y, which is the left homotopy between HF and H. Then there exists K, which goes from B prime to X, and which is a left homotopy between F and G, and it is constructed from the following diagram. So we have an inclusion of two bottoms of the cylinder into the cylinder. We have a map F plus G here, and we have our trivial fibration here. Then we just consider the lift, and this lift gives us the desired left homotopy between F and G, which shows that H star is in fact a monomorphism. Okay, now for the final part of this proposition. So assume that B is a cofibrant object, and we have two left homotopic maps, and we have a left homotopy from B prime to X. Then, first of all, we see that the map from B to B prime, I0, or I1 for that matter, is a trivial configuration. Well, we established this before. And assume that we have some path object for X. So here we just have some with equivalence. Here we have a vibration onto X times X. Then there exists a lift in the following diagram. And so this lift J gives us the desired right homotopy between F and G. So we just put K B J I1, and this is a right homotopy between F and G. So this finishes the proof of the proposition. And well, we established several important properties of left and right homotopy. Now let's derive two corollaries from this proposition. First corollary states that if M is a model category and B is a cofibrant object and X is fibrant, then the notion of left and right homotopy coincide in their home set, and they're both an equivalence relation. Both equivalence relation. Additionally, if F is homotopic to G, then there exists left homotopy between them for any cylinder B prime, and right homotopy for any path object X prime. Okay, and the second corollary states that the relation of being homotopic is an equivalence relation on morphisms in model category. Sorry, not in model category, in full subcategories spanned by fibrant and cofibrant objects, and it is compatible with the composition. So we've proven that if we compose two homotopic morphisms with another morphism in arbitrary order for fibrant and cofibrant objects, they remain homotopic, which means that so it is compatible with composition. And this means that the category MCF module of this equivalence relation is well defined. So this notation means that just that objects here remain the same, and morphisms are modeled out by this equivalence relation. Okay, this is the same as MX. Okay, so we clearly see that the functor which goes from MCF to this quotient category, so to speak, inverts homotopy equivalences. However, we wanted to invert weak equivalences as well. So I want delta to invert weak equivalences as well. And as it turns out, it actually does invert weak equivalences. So we have the following proposition, which can be regarded as an analog of Whitehead's theorem for cellular complexes in algebraic topology, namely that a map between cell complexes, which is a weak equivalence, i.e. it induces an isomorphism on homotopy groups, is in fact a homotopy equivalence. So here we have the following statement. Assume that M is a model category and alpha is a morphism in well, a weak equivalence between fibrant and cofibrant objects. Then this is equivalent to saying that alpha is actually a homotopy. Or equivalently, delta of alpha belongs to isomorphisms in this category. So let's prove this. So let alpha be as in the formulation of this proposition is a map between A and B. Then we can apply Ken-Brown's lemma to this functor here. Sorry, to this functor. Yeah, it's this one. So by the proposition above, if X belongs to, well, is fibrant and cofibrant, then alpha star is an isomorphism. And we can assume that, well, okay, so let me write this down. So we have so we have an isomorphism like this. We can put X to be B. Then there exists beta, which is just alpha star minus 1 from the identity of B, such that the composition of alpha and beta is homotopic to the identity on B. Well, it is equal as homotopy classes, which means that alpha beta is homotopic the identity on B. In particular, this implies that alpha beta alpha is homotopic to L. Now we can put X to be equal to A, and we find that beta alpha is in fact homotopic to the identity on alpha. Why is that? Well, simply because if we have a map like this here, and it is alpha beta alpha star, which is equal to alpha star. Then we see that well, at the moment, yeah, we see that alpha star of the identity on alpha is the same as alpha beta alpha star from the identity on alpha, which means that well, I'm not even sure that I need this because, oh, in any case, alpha star is an isomorphism, so we can cancel it out, and we see that beta alpha star is the same as identity on alpha, which means that the alpha is homotopic to the identity on A. Okay. So yeah. Okay, so now let's prove the converse statement, namely that if we have homotopy equivalence, then it is in fact a weak equivalence. Okay, so firstly, oops. We want to see that F is in fact a weak equivalence. So we factorize F as a trivial cofibration followed by a fibration, and we want to show that P is in fact a homotopy equivalence. As we well observe that C also is fibrant and cofibrant because it fibers over B, which was fibrant and cofibrant, and we also have a cofibration from A to C, where A is also fibrant and cofibrant. This implies, by what we've just shown above, that G is a homotopy equivalence. Okay, and we want to show that P is a weak equivalence. So assume that F prime is a homotopy inverse of F, and H from B prime to B is in fact homotopy between F prime and identity on P. And consider H prime, which is the lift in the following diagram. So this is just a notation that this is the lift between these two maps. In more detail, we have B to B prime with equivalence. Here we have GF prime. Here we have H, and here we have a lift H prime. Now denote by Q H prime I1 is the map from P to C. Clearly, PQ is the identity on B. And H prime is a left homotopy between HF prime and Q. Now assume that G prime is a homotopy inverse to G. This in turn implies that P is homotopic to G times G prime. And This is in turn homotopic to Fg prime because Pg is homotopic to F. Well, sorry, G is just equal to F, and hence homotopic. This in turn implies that thus Qp is homotopic to Gf prime. So Q was homotopic to Gf prime, as was shown before, and times Fg. Fg prime. So P is homotopic to Fg prime. Now we observe that homotopy inverses cancel each other out, and this is thus in turn homotopic to the identity on C. This implies that Qp is a weak equivalence. Indeed, if K is a homotopy from one, so we just established that it is homotopy to weak equivalence. We didn't show that it is in fact a weak equivalence. However, assume that K is a homotopy between the identity on C and Qp, then Ki0 is equal to the identity on C, hence it is a weak equivalence. And I0 is also a weak equivalence because it is an inclusion of the bottom of the cylinder into a cylinder. Okay, thus it follows that K is itself a weak equivalence, which in turn implies that Ki1 equal to Qp is a weak equivalence. I1 is also an inclusion of a bottom of a cylinder into a cylinder, thus it is a weak equivalence. Finally, it remains to observe that E is in fact a retract of Qp. Why is that? Well, we have the following diagram. It remains to observe that, well, weak equivalences are closed under retracts, which means that E is a weak equivalence. Thus, we have shown that homotopy equivalences between fibrant and cofibrant objects are precisely weak equivalences. Now we can derive a corollary from this. I think I don't have much time left, but I hope that will suffice to conclude this. Okay. So corollary looks like this. So let M be a model category and consider functor gamma, which goes from MCF to the homotopy category of MC. Recall that MCF is itself a homotopical category, thus homotopy category is defined. And delta is a functor which goes from MCF to its quotient by homotopy equivalences. Then there is an isomorphism of categories. So it's even better than an equivalence of categories. It's an isomorphism of categories. J, which makes triangle diagram compute. And J is identical on objects. Okay, let's prove it. And to show that MCF modular equivalences satisfies the universal property of homotopy category. So we see that delta maps homotopy equivalences to isomorphisms. Well, actually, they coincide. And by proposition which we've just proved, delta maps weak equivalences to isomorphisms. Now assume that F is a functor from MCF to D such that F inverts weak equivalences. Then consider a cylinder like this, denote this by S. We see that SA0 is equal to SA1 is equal to the identity on A. And since S is a weak equivalence, it follows that F of I0 is equal to F of I1, and it is an isomorphism. This in turn implies that if H is a left homotopy between alpha and beta, then f of alpha is equal to f h capital f of a0 is equal to fh f of a1 is equal to f of, which means that f of alpha is equal to f of beta. This means that left homotopy, or since these objects are fibrant and cofibrant, just homotopic maps are mapped to the same thing under the functor f, which means that there exists a descent of this functor to this quotient category. So we in fact have functor g such that g delta is equal to f. And moreover, g in objects is the identity. And well, alpha is mapped to f of alpha. Now it remains to just use the uniqueness of the homotopy category, show that there is a unique J isomorphism. Categories. So this shows that the homotopy category of MCF can be computed using the quotient under homotopy equivalences. And so this leads us to what is sometimes referred to as fundamental theorem of theory of model categories. Theorem. Which states the following. So assume that M is a model category and gamma is the localization functor, and U and R are cofibrant and fibrant replacements respectively. Then, first of all, the inclusion of MCF to M induces equivalence of categories of the following form. And this quotient category is isomorphic to homotopy category, is equivalent to the homotopy category of the whole model category. Second, there is a canonical isomorphism. Goes like this. So we take MQR QRY modeled by the homotopy relation. This is isomorphic to set in the homotopy category between X and Y. And this is isomorphic to morphisms between fibrant and cofibrant replacements applied in the reversed order, modulo the homotopy relation. And this is also isomorphic to this set. And if X is cofibrant and Y is fibrant, then it is isomorphic. Then we have an isomorphism between morphisms in homotopy category and just morphisms between X and Y modulo the homotopy relation. In particular, this means that the homotopy category of a model category is a category without passing to a higher universe. Finally, the localization functor identifies left and right homotopic maps. And to conclude all this, it is the saturation property of model categories that F between A and B is mapped to an isomorphism in the homotopy category if and only if F is a weak equivalence. So let's prove this theorem. Well, the first part follows from what we already done. It was proven above. The second part, well, also was proven above. So basically, the third part too. The only non-trivial thing remaining to prove is that well, it's the saturation property. So assume that we have a morphism which is mapped to an isomorphism. Then QRF is an isomorphism in this category, which in turn implies that QRF is a homotopy equivalence. Which in turn implies, since we passed to the subcategory of fibrant and cofibrant objects, that QRF is a weak equivalence. And since Q and R reflect weak equivalences, meaning that a map is composition of Q and some map is a weak equivalence if and only if the initial map was a weak equivalence. It follows that F was initially a weak equivalence. Okay. So let me conclude this with the following. So I will conclude my talk with the following corollary. Which follows from part 2 of the theory. So let M be a model category, gamma be the localization function. Then for any two objects, X and Y in M, first of all, function which assigns each zigzag X R a map gamma R minus 1 gamma F gamma inverse from X to Y in the homotopy category. Induces an isomorphism. Well, maybe it's better to say bijection. With maps from X to Y in the homotopy category. Yeah, induces a bijection with maps from X to Y in homotopy category and classes of equivalence of such zigzags where two zigzags are equivalent if they fit into the following square. So here is a zigzag. It should fit into the following square. So here all horizontal maps are, so here all maps on the sides are equivalences, hence all vertical maps are also equivalences. And we say that two zigzags are equivalent if they're the top and the bottom of this diagram. So just to comment a bit, it explains the significance of the localization in the context of model categories, because for arbitrary category and subcategory, the localization is constructed from zigzags of an arbitrary length. And here it is sufficient to consider only zigzags of length 3 to obtain all morphisms. So this is an explanation of the fact that we don't need to pass through a high universe, for example, and well, why model categories are so convenient for localization. And the second part of this corollary is that if we have a map between two objects in a model category, then morphism gamma f in homotopy category corresponds to a zigzag of length 3, where we have f in the middle and two identity morphisms on the sides. Okay. So this is it for today, I think. Next time I will talk about equivalent functors, derived natural transformations in more detail. Thank you all for coming. Maybe someone has some questions, suggestions, comments.